Chapter 15 deals with radical reactions. We've talked a little bit about radicals back early on when we were talking about mechanisms and how they form in terms of the single-headed arrows and such. And we're going to talk much more about their reactions now. So the first question would be, what is a radical? And introducing what radicals are. Radicals are atoms or groups of a molecule that has an unpaired electron. And these are reactive, so we can't put them in a bottle very easily. And so that we refer to those as reactive intermediates. And it has a single unpaired electron. And the way that that electron forms is homolytic bond cleavage. So here is the basic diagram of breaking apart a covalent bond and putting one electron onto each atom where the bond is breaking. In terms of the structure of a radical, well, if you think about it, we now no longer have an octet on that carbon. And in general, we deal with carbon radicals. We can talk about any kind of atomic radical, but in terms of organic chemistry, we're going to talk about carbon radicals. And what essentially the way you can think about it is that these are trigonal planar structures with an sp2 hybridization, and that unpaired electron is sitting in the p orbital that is not hybridized. And so the hybridization, the hybrid orbitals, which are shown here, the hybrid orbitals create the bonds, and the p orbital is where that radical is going to reside. In terms of stability, the way that we can learn about the stability of different types of radicals, and real quick going back, we can talk about primary, secondary, and tertiary radicals, which relates how many carbon-containing groups are bonded to that radical. And that is what that primary, secondary, tertiary is for. In terms of stability, we can talk about bond dissociation energy, because the question is, how easy is it to form these radicals, or how difficult is it? The stronger the bond, the more difficult that you're going to see that. And so we can use the CH bond to measure that stability. And so this allows us to, again, calculate the amount of energy required, and breaking stronger bonds requires more energy. And so if we look at this example here, okay, the secondary radical is more stable because less energy is required to produce it. It's easier to produce. So you can see both reactions are endothermic. So 397 for secondary, 410 for the primary radical. And so it's easier to form the secondary radical, and therefore it is more stable. It's easier. And so you can see this with this diagram here. Okay, if you look at it, the starting materials are going to have the same energy. The secondary radical is going to be at a lower energy because it is easier to create. And therefore, the stability of radicals goes methyl, primary, secondary, then tertiary. Okay, very similar to carbocations. The one major difference here is that radicals do not rearrange. They never rearrange. And we can get carbocation rearrangement to make a more stable carbocation. And so this is something that can tell us a little bit about mechanism of a reaction. If we have rearrangement, it's not a radical reaction, and we're sure of that. In terms of the general features of radical reactions, light or heat is what's used to make these reactions go. Sometimes you need a radical initiator to start radicals forming. And these are generally peroxides. Okay, and so those are the types of radicals. And if you heat a peroxide, or again, you can use light also, and you can break that weak OO bond, which is going to give us a radical. And there are two major types of reactions, and we can either have the radicals react with sigma bonds, or they can add the double bonds. I'm going to show you an example of that And that will then end this little mini lecture. And so if a radical reacts with a CH bond, okay, essentially it's abstracting that hydrogen, okay, and it then abstracts it and it leaves a radical, okay, a carbon radical. And so a diagram to show that is here, where again, X is the radical that is formed. It can then react with a sigma bond. One electron from that sigma bond goes to bond with the one unpaired electron in the radical, leaving a new radical here. And it's a carbon-based radical at that stage. And so that is one type, and that's with the sigma bond. So you can have abstraction with a sigma bond. You can also have a reaction with pi bonds, okay? And what will happen is essentially it's an addition reaction where one of the electrons from the double bond is used to create a new sigma bond, and the other electron then goes to form the new radical. And so again, a new radical is created either way. It doesn't matter how we slice that. Either way, we're creating a new type of radical. Now, it's possible, and this is where it can be important, oxygen can be considered a diradical and it can inhibit. So if two radicals come together, you can then basically kill the radicals, and oxygen is one way of basically quenching a reaction or inhibiting a radical reaction. So a lot of these have to be done without any oxygen around. And so again, the oxygen causes these reactions to slow down. And anything that does that is referred to as a radical inhibitor or a radical scavenger, something that scavenges the radical and essentially kills that radical. And so that's where we're going to stop in this discussion. We'll continue discussion with future videos.